Hello, everybody. The next talk is Wily Python, Writing Simpler and More Maintainable Python by Anthony Shaw.
Hi, everybody. My name is Anthony Shaw, and I'm giving a talk about simplicity and trying to write more simple Python. This is my first time speaking at PyCon. I'm super nervous, and I was researching some tips about public speaking for this kind of event, and I found 3 rules. Rule number 1 was to have frequent pauses. Rule number 2 was to never start with an apology. And then rule number 3 was to never thank people for coming to your talk and just assume that they're here to listen. So thank you for coming. We've got a lot to get through, so I'm going to go quickly, so I apologize for that. And we're going to talk about code complexity today. So what does that mean? How would you inspect if your code is complicated? And then we're going to look at not really just how is your code complicated, but how do you actually measure that? Because everybody thinks that they write simple code because it makes sense to you, but it's more about communicating with other people and sharing your code and your ideas with others. So we're going to talk about code metrics, and we can then talk about how do you actually simplify the code once you realize whether or not it's complicated. And the title of the talk is about Wily Python. So I'm going to introduce a tool called Wily, which I wrote, which basically helps you manage this process of understanding whether your code is complicated or not, by what measure, and how do you simplify it, and then basically doing that in a loop. I know there's probably quite a mixed audience here today, so in terms of the complexity of the talk itself, this is quite meta. I think the first section is really kind of a beginner level, and then the second part is intermediate to advanced. If anyone has any questions, please come and speak to me afterwards. And if we get time later in the talk, we can open it up for Q&A. And also, I've written an extensive article on this topic on realpython.com as well, which takes about an hour and a half to read. So it's probably one of my shorter articles. I encourage you to read that because there's a lot more detail in that post. Okay, so I now need to convince everyone that simple code is good. So why should you care if your code is complicated or simple? So remember that your code is written not just for computers, it's written for humans. And Python especially is almost written in a language that's easy for people to understand. And when you write an application in code, you're leaving instructions for the computer, but also for your fellow developers. So not just in code comments, but in the actual code itself, in the way you name your functions, your classes, your variables, the way you structure it, it should be a set of instructions for people. So it should be clear that what you're trying to achieve and what you're trying to do with the code, which is why you want simpler code rather than more complex code. Also, code is a living thing. It changes often. So if your code is complicated to understand, when people want to make changes to it, they're more likely to misunderstand what it was you were trying to do and introduce bugs. So you want simple code because it's easier to maintain the code, it's easier to adapt the code, and it's easier to add more functionality. And then lastly, complicated code is hard to test. And testing is good. Hopefully we can all agree on that. So you want simple code so that you can test it, so that people can understand it, and so that you can adapt it over time. So how do you measure if code is complicated? So this really simple sample uses the crudest measure for measuring the size of code, and that is the lines of code. It's really easy to calculate the number of lines of code we have in this application, and in theory, you want fewer code, so you'd want fewer lines of code. But I can represent that same code example in fewer lines of code, but there's one massive issue with this example. So I've used a few funky Python syntax here. It basically does exactly the same as this, but it's on 3 lines. So there's less code, so that should be a good thing. But as Tim Peters famously said, readability counts. So lines of code is not really a measure of complexity, but more about volume. You're really looking at how big the application is, and encouraging people to write less code can actually encourage the wrong behavior, because people end up condensing stuff down to a point where it's less readable. So lines of code doesn't really talk about complexity, it's just about volume. And there are other measures you can use for complexity. One of those measures is called cyclomatic complexity. And I want to explain it in terms of ordering a burger at McDonald's at a drive-thru. So you start off with one decision, which is what do you actually want to eat? So let's say you want to eat a Big Mac, and there are other burgers available from other restaurants. So you start off with a cyclomatic complexity of 1. You've made one decision. They then asked you, do you want to make that a meal? So that increases the complexity by 1. They then say, what size do you want? That's another 1. What drink would you like? And then if you want diet or regular Coke with that. So the cyclomatic complexity of ordering a Big Mac from Macca's is 5. So if you imagine you went to McDonald's and they asked you 16 different questions, at which point would you say it got really complicated? So cyclomatic complexity is like this, because when you're trying to read a piece of code, you've got to understand all the decisions and how they get made. And I picked this code example. I apologize if it's a bit small. This is actually from the Python standard library in a module called localpi. So every time in Python there's an if, an else if, a for, try statement, it counts as increasing the cyclomatic complexity by 1, because that's a decision that's got to be made in code. So why does that have to do with complexity? Well, when you read this code sample, and if I ask you to articulate what this does, you're not just reading down a set of statements, you're actually looking at each if block and thinking, okay, well, what would that variable be? If it's this, then that happens. If it's this, then that happens. And you've got to store in your head basically like your own value stack and start to evaluate the code. Whereas if it's just a series of flat statements, you can see one by one what that code does. So this is a complicated piece of code. It has a high cyclomatic complexity. It does take a bit of time to read and understand. But there's also, I think, an easier way to see cyclomatic complexity. If you turn the code on its side and then get a pen and draw a line around the white space, you'll see this. So I'd say that instead of just trying to calculate cyclomatic complexity, if your code looks like a mountain range when you turn it on its side, then it has a high complexity. And also another quote from Tim Peters, flat is better than nested. So flatter code is easier to understand, is easier to process. And this example has a high complexity. So you could walk into this and think, okay, well, let's just make it flatter and simpler. But I think you're missing one principle, and that is there's actually wisdom in complicated code, and I will talk about this as well. So most IDEs have a git blame tool. If you've ever used git blame, I've turned on git blame on the same module, but just a few more lines down. And you can actually see here who and when and why each piece of code was changed. And we've got changes from 19 years ago, 15, 12, 6. Every time somebody has to fix an issue, fix a bug, add an edge case, they go in and they make that change. So that's normally in the form of an if statement or a small change, which therefore increases the complexity of the code. So just trying to charge in and say, let's just make this simpler, you actually need to understand all the reasons why the code is like the way it is. The other thing you might miss is if you don't introduce this, you could reintroduce bugs which have already been resolved, which could upset users. So to simplify what I've just said, when you start off with a new application, you typically have a little amount of functionality and a few users. So you should have a little amount of code and a small amount of cyclomatic complexity. As you add more features, you tend to write more code. So the lines of code measure will go up. As you have more users, you have to support more edge cases, more platforms, more scenarios, and you tend to increase cyclomatic complexity of the code as well. And then a double whammy is when you've got a lot of users and a lot of functionality. So CPython itself is a good example. It's used by millions of people. It has a lot of users, it's got a lot of functionality, So it has a lot of complexity. So if lines of code and cyclomatic complexity can't really be used as measures for big applications, what can you use instead? So I'm going to talk about Halstead metrics. I do warn that there's a bit of math in this section. So if you feel like the math is a bit too complicated or outside of your comfort zone, don't worry, there are tools that can calculate this stuff for you. This metric has actually been around since 1977, predating Python. And the research behind it as well is very old by this point. How many years is that? 50 years? So the research behind this is actually 50 years old, just over 50. Okay, so let's introduce two things. There's a value called operands. Operand is the sum of the values you've used and the sum of the variables you've used. So the number 1, or a string constant, would count as a value, and a name would count as a variable. So if you add all of those up, you get operands. If you add up the amount of built-in syntax you've used in the application, that's called operators. If you take the sum of the operators and the sum of the operands you've used, you end up with a measure called length. And if you take the amount of unique operators you've used and unique operands you've used, you end up with a measure called vocabulary. So this probably sounds a bit complicated compared to lines of code, which is quite an easy way to measure things. But there's reasons behind it. So if anyone's familiar with the abstract syntax tree, it's basically what happens when your code is compiled, is turned into a tree, and then it's interpreted as a tree. So this simple code example I've got here with a function with 3 statements. I'm going to assign the value 1 to a variable called a. I'm going to increment that by 1 and assign it to a variable called b, and then I'm going to return b. So in the tree, you've got the 2 assignments, and then you've got the return statement. In the first assignment, you've got the name, which is the variable a, and the number, which is the number 1. So everything in green would be added up, and then everything in yellow would be added up to give you operators and operands. And then this is where it gets slightly more complicated, unfortunately. We've then got volume and difficulty. So you multiply the length by a logarithm of the vocabulary to get volume, which is better than lines of code. And then this one had me stumped for a while, but basically it more or less tries to calculate how you've reused code and how much code you've used to achieve something, and then gives you that as a variable called difficulty. And then lastly, you get effort, which is a multiple of both of those two things. Okay. So all of that's very theoretical, but basically there are better ways of measuring the amount of code in an application and the amount of variables you've used and the amount of syntax you've used. So all these things are really just basically a way of measuring the amount of code you have. There's actually a better measure than this. Don't worry too much about the equation. There's different versions of this equation, but this is called the maintainability index. And the output is just a number from 0 to 100, and it's a scale. So if you run the maintainability index over your code, it will just give you a single number. If that number is between 0 and 25, it means your code is unmaintainable. It's a bit of a mess. If it's between 25 and 50, it would be like my high school teachers say, cause for concern. If it's between 50 and 75, that's realistically where most applications are, but you can still definitely see improvement. And then if it's over 75, I don't believe you. So this metric is actually used in Microsoft applications, in Java applications as well. And in Python, this is the equation we're using Wily for calculating the index. So if you don't want to go and sit and calculate that by hand, basically it's taking the Halstead volume, the cyclomatic complexity, and the number of lines of code. So your maintainability index is going to be lower if you've used a lot of code, a lot of variables, a lot of syntax, and a lot of nesting to achieve something. That's when you're going to have something in the red. So it's going to be in the green, where you've got nice flat code, you don't have too many functions, too many variables, and there's not that much code volume. So that's where it's going to be in the green. So you don't have to calculate this stuff by hand. You can use a package called radon. On the command line, you can run radon, and then the algorithm that you want to use, so CC is cyclomatic complexity, and you give it the file name you want to run, and it will basically calculate the number for you and give you that output. You can also do MI, which is the maintainability index I just spoke about, and it says that my application was 87.42, which is pretty impressive, but it's only 4 lines of code, so that's understandable. And then lastly, you can run HAL as the algorithm, and it will give you all of the measures I spoke about. It also outputs another one, which I've cropped from the image, which is actually the number of bugs it's spotted in your code. Halstead actually theorized that you could calculate the number of bugs based on the amount of code, but this theory was 50 years old. So, okay, so you got the numbers. You look at the numbers and you think, okay, that's interesting. I've got a vocabulary of 9 and a calculated length of 20.26. What now? So does that tell you whether your code is maintainable or not? So really, I was looking at this problem, and this is where I came up with Wily. So Wily is a tool that basically looks at the way that the maintainability of your code, the complexity of it, changes over time. So it assumes that your code is in a Git repository, and it will go back through the Git history and basically run complexity metrics over each revision. And it will then store that in a flat file database, and it will let you query that and see trends of maintainability and complexity in your code applications. So I'm going to give you a demo of this. And because I don't trust live demos, I'm going to do magic hands. So the way that you run Wily is you run Wily build and then give it the path to your application. It will go and check out all the revisions in Git and then basically go and run metrics over them. So the Halstead metrics, the cyclomatic complexity metrics, lines of code, all of those sorts of things, and put those in a database. So it's quite straightforward to get started with Wily. It's also really useful for test applications, which I'll talk about later. You can just type Wily index, and it will give you a list of all the Git revisions that it's checked out. And then when you run Wily Report with the name of a file, it will give you a table with some metrics in it. So each line is a Git revision. And then if the complexity changed for any reason, so the maintainability index went down here, you can see the amount that it went down, and the cyclomatic complexity increased. So this is useful for basically looking at specific files and seeing how they trend over time. You can also use it as a pre-commit hook. So when you're making changes to code, if you run Wily diff, it will actually go and show you how the complexity of the code has changed for that particular file. So if you use it as a pre-commit hook, basically when you run git commit, it will go and look at all the changes you've made in code, and it will print out to the screen whether you've made the maintainability of the application worse, the cyclomatic complexity, and it will give you that down to a function level. So in this case, I've just added a test function called test8, which just adds a few lines of code and another test case. So it's going to go and print that information for me. And then lastly, you can graph any of these metrics. So if I were to graph my test file, and I wanted to look at the maintainability index over time, then it's going to print that out for me in an interactive graph. And each point on the graph will actually be the Git revision and the reasons why, and also the author of the Git commit. So for this is a small toy demo, but for a big application, you can use this. Let me try it for another one. So I can see how the maintainability index of my code has changed with each Git commit. And then lastly, you can combine metrics together. So if you wanted to look at maintainability index and lines of code, you can give it multiple measures, and it will add a second metric as the bubble size. So I can basically look at how my code has changed over time. Okay, so using Wily, you can track the complexity of your code, and then you can start to refactor it to make it simpler. There's something else I wanted to point out, which is that when you start to look at complexity in your applications, you're going to find that some of your modules, some of your files, have a complexity which is far higher than some others. And the reason behind that is that complexity has its own gravity. So if you've got a function which you've started to add edge cases to, as your application matures, you're going to find yourself adding more and more edge cases to that function. If you've got what they call like a God class or something, or a module that basically ends up catching every kind of situation, that will draw more and more complexity. So I wanted to point out this principle because I think it's important when you start to refactor, is that one of the things you need to start to do is to spread complexity around in your code, break it up, and follow something called the single responsibility principle. The single responsibility principle is that any function, any piece of code should have one responsibility. You shouldn't have a piece of code which is trying to achieve everything, because then it becomes unmaintainable, it has too many characteristics, and it becomes very hard to test. This lovely creature is the cane toad. Is anyone here from Australia? One at the back. You probably recognize it. So the venomous cane toads were introduced in 1935 to Australia in the hope that they would control the destructive cane beetle population. So why am I talking about this? They turned out to be really bad at controlling beetles, but remarkably successful at reproducing. They also have no natural predators in Australia. So basically, they've infested Queensland, the northern state. And the reason I point this out is because when you're looking at refactoring code, if you don't have a good test suite, because I think that the testing coverage of the cane beetle population was quite poor, there really wasn't a good understanding of the complexity of the actual environment. It just thought this would be a quick fix, and we can sort this problem out. So high test coverage should be a given before you start refactoring any application. However, high test coverage doesn't mean you've checked all the behaviors. So when you're looking at refactoring an application, you need to understand all the ways in which the application can behave so that the new code behaves in the same way as the old code. Testing is one way to do that. Another way is to help your users to find the bugs for you. And then lastly, one of the difficult situations you might find yourself in is when you're refactoring, actually coming across a bug. And not just a bug, but a known bug, and a bug that's expected. So if anyone's ever faced this before, it's one of the most fun and challenging things in refactoring. It's where you've refactored a code base and you've come across this and you think, how could this ever work? And you realize it doesn't work, and it has a side effect which makes something else work. And the only way to refactor it is to either reproduce the bug in your new code, solve the problem and explain to all your users why you're breaking compatibility, and there's a third option, but I don't know what it is. So this is a really tricky one to look out for, but like I say, testing is critical. So I guess in conclusion, Wily can benefit you in tracking complexity in your code base and measuring that over time with the principle that you're going to improve it. Complexity measures are long-term. Just calculating the complexity of your application is interesting, but the whole point is that you want it to improve. And make sure you've got good behavioral test coverage. There are some tools you can use to do this. PyTest obviously is great as a test suite, and there are some coverage tools for PyTest, but they just look at line coverage. They don't actually look at the way you're testing different behaviors. There are some automated tools to do that, but really the best way to do it is to look at features and functionality, to describe those and make sure you're testing each one of those features. refactor often. This shouldn't be an annual event that you sit down and say, let's clean up our code base. This should be something that's done frequently. And if you refactor your code often, you'll find that the amount of refactoring you have to do, the amount of yak shaving, the amount of edge cases you have to deal with is far smaller. So if you think about measuring complexity using a tool like Wily, and you can see sprint by sprint or day by day how that is increasing or decreasing in your code, that should encourage your team to refactor. And then lastly, divide and conquer. If you're going to refactor any substantial code base, it can be very daunting at first. So my advice is to start with something small. Start with something that's got good test coverage and something that you understand, and refactor that one module first, and then work your way out from there. Don't try and rewrite the entire code base in one go with the intention of improving simplicity. Everyone starts out with the best intentions, but you might find yourself with a population of cane toads. So that really wraps up my talk. If you want to read more detail on techniques for refactoring, there's an article on realpython.com that I wrote to explain this. If you want to check out my website, it's on GitHub. If you have any questions and you want to email me, that's my email address. And if you want to tweet me, then that's my handle. And we have 5 minutes remaining for questions, so thank you very much.
Anyone that has questions, please come to this microphone. Oh, there's actually a microphone back there too. So go to any microphone. Go ahead.
Oh, okay. Sorry. I thought you were getting something. What is Wily? How do you get it? Is that a product or?
It's a package on PyPI, so just pip install Wily,
Okay.
and you can run it on the command line.
Awesome. Thank you.
Cool.
Hi. The equation for the Halstead
Yeah.
thing, I can't remember what it's called. There was a constant in there. There's like 171.
Yeah.
What was that?
I've got no idea.
Okay.
Hi. The examples that you showed with Wily, they seem to operate on a single file. Is it possible to run it for an entire project, or do I have to do it in a folder?
I toyed with this, but yes is the answer. You typically give it the path to your whole project. And if you want to run a report on a folder, it will give you the metrics for every single file, or you can roll them up into a single metric. It's designed for big applications, but I just used it for a tiny sample. Otherwise, it would take too long to compile. Yeah.
Thank you.
Cool.
Hey, great talk. Loved everything. Question. I agree with everything you're saying. How do you get team buy-in?
I think if you look at the times when people have to make changes and they appreciate that complexity makes it harder to make change, if you pin them down then and see, this is why we need simpler code, I think that's probably the opportunity to do it. If you phrase it as let's have a massive refactoring of our code base,
Right.
and you're basically going to put yourself in a position where you're going to have unusable code or a branch that doesn't compile, or whatever, however you measure that, for multiple sprints, that's a really hard sell. So it needs to be a small piece of work.
Right. Cool. Thank you.